I'm here from Materialize Inc. I'm the chief scientist at Materialize. We are building something which I'm going to tell you about now, or I'm going to tell you my take on what we're making. There's some contact information up now. There'll be some links and stuff as we go, but there's all this information will be again at the end of the talk, so don't get stressed out at the moment about grabbing anything down or wandering off onto your phone. So what I'm going to tell you about that we're building at Materialize is what we call the SQL View Maintenance Engine. It's the title of the talk. That's me at Materialize. And perhaps some of you are scratching your head, perhaps not, but perhaps some of you are scratching your head saying, what's a SQL View Maintenance Engine? And so I'm going to talk through that. I'm going to talk through how it comes to pass, why you might want such a thing, what sorts of problems does it solve, and what opportunities does it open up that you might not have imagined before and you might start scratching your head and thinking about now. So many of you are probably familiar with Relational Database. So this is something like Postgres or MySQL or something from Oracle or IBM or what have you. I've drawn it here as just a generic relational database management system. I put it in red because these things are usually pretty hot. They're pretty busy. They're doing a lot of important business stuff for you. Typically, these are handling things like your business critical reads, writes, transactions. When customers show up and they make purchases, you write stuff down. If contact information about your customers changes, you write that down. You want all these things to be consistent. This is, in many cases, your source of truth for all of your important business data. Now, at the same time, in addition to doing these sort of interactive reads, transactions, writes, stuff like that, these databases are also managing another class of workloads. These I've drawn them a little bit differently with bigger arrows because they're a bit meatier and chunkier. These reporting and analytics and monitoring tasks. So you're asking questions like, how many engagements did we have in the past 24 hours? Maybe you're monitoring some of your system infrastructure, so you're wondering, what are our KPIs? What are our latencies that we're seeing when we're handing numbers back to people? Just other analytics that you might be looking at. So opportunistic, when people buy a foo, what do they also buy in the same shopping basket? We want to try to figure those things out so that either you sell more things and make more money, or you learn a bit more about your customers. But this is a class of workload that is, I would describe it as a little less, in this picture at least, a little less interactive. You're not interacting with a hot database. You're sort of landing on it and asking a big query and getting the answer back. And sort of in the modern era of, let's say, data warehousing type things, the data, these queries land not so frequently and refresh not so frequently. And we're going to see if we can figure out how to change that. Now, the current state of the world, at least one of the current states of the world that we hear from a bunch of folks, is that if you want to address this problem, more and more analytic queries of more and more complexity, people, the current tools, for sure in the database spaces, aren't great for this. So people move towards denormalization, if you're familiar with this. You take all of your exciting records about interactions that people have had with you, and instead of saying, here's a customer ID, go look up the customer later, you blat down everything you know about the customer right in line in these records. You make relatively big, wide tables of all of your interaction, so that when you come and do these analytics, these reporting things, you just aggregate up, running through all of this data. You count up for every state or something like this, the amount of sales you've done in it, and you were lucky that you wrote down the state instead of just the customer ID, because that would have been a join, and those are hard and whatnot. So a lot of people tweak their internal data architectures to look more like this denormalized form, a little less like a relational database and a bit more like what's going to be amenable to a stream processor, which is fine. Like, there's nothing fundamentally bad about that. It causes some challenges. So the good thing that happens, I should say, is that you're now able to cache a fair bit more. You're able to push this denormalized data out so that these queries that come in can land in the cache data, and instead of performing a complicated multi-way join in your relational database, can just read some data right out of your cache and serve some answers up. The flip side, the problem though, is that life becomes a little bit harder for everyone on the left side of the screen. So these reads, transactions, and writes have a lot more work that they need to do when data changes. So like if a customer changes their contact information, they move from one state to another, you have the potential need to go rewrite all of this data in all of these places that you scribbled down your specifics about each customer. It would have been helpful in that setting to have left this as a customer, basically primary key from some customer to all of the information we know about them, and not have expended everything out in place. So in a lot of settings, this leads to ossification. Basically, it's hard to change things. If someone shows up with a new, exciting bit of information they'd like to write down about customers, maybe you have some engagement score that you're trying out. If you have to scribble that down in every single place that the customer is used, that's a lot of work to go and do, and it makes it hard for that person to try out a new feature. Similarly, someone comes in with a new query and says, I'd love to look at Our data aggregated this way we hadn't realized we'd need before. If the data isn't laid out correctly, if it hasn't been denormalized appropriately, maybe that's a non-starter. Right? Maybe it requires a lot of data engineering to put that into place. So this is, this can be a bit of an awkward pickle here, where you want to both support these relational database interaction modes and also larger aggregate queries with prompt, sort of interactive vibe to them as well. So that's what we're gonna talk about. We're gonna talk about taking this diagram and spinning it around a little bit in a way that hopefully you might have imagined in the streaming space. We're gonna let you think of a relational database still as a source of truth. So people are interacting with this, still using their reads and their writes and their transactional updates. But rather than try to land analytic queries onto the relational database, which isn't exactly designed for this, we're gonna think instead of the database as producing exhaust. It's gonna be producing in different language, change data capture, or it's going to be producing a change log or a bin log. Basically, we're going to get a record of what's happened in the database, what records have been added and removed to each of the various tables. And we're going to feed that into a data processing engine. This is going to be Materialize for this talk, though I'm sure all of you are familiar with other sorts of platforms. What I'm going to be doing for most of the time in this talk is calling out the exciting ways that Materialize is going to be different from these things you might be used to using. And some of the cool things that you can do with it that other frameworks, aren't quite at yet. So I'm going to try to get you excited about that and tickle your brain and get you thinking about, like, wow, I could do this, that, and the other thing that I've never been able to do before. That would be a total success. So let's start, actually. What I thought I would start with, what I really thought I would start with is a live demo. And I'm not going to do that because it was implied that maybe that's an irresponsible thing to do. So what I've done instead is I've captured a demo. Yesterday I just started walking through some examples in our system against a live running installation. I'm just going to walk you through essentially a little video of this. So Materialize presents in a few different ways. It presents as a database, and one way you can interact with that is through just a SQL shell. So we have a CLI here that we use where you log in and you get essentially something like, if you've used pSQL or these other sort of CLI tools, it's just an interactive setting where you can look around. You can look at, in this case, sources. These are places we get data from. For example, all of the MySQL things are a bunch of relations we've pulled in from a MySQL instance nearby, and they're showing us a bunch of data inside them. This is there's also some logging stuff that we have here. Don't get too excited about any of the specifics here. But as you can see, one of the things that you can do is just treat this as a SQL instance. So you can count the number of records in each of these relations. In this case, order line happens to be one of the big relations in the TPCC benchmark. This is a transaction processing benchmark, and the order line thing is tracking a bunch of different orders that have flown through, or parts of an order that have flown through some big warehousing system. And we're counting the number of records in it. And you can see that some million odd records. This isn't a particularly big installation. Some million odd records, and it takes about half a second. And there's no particular reason to think that that's great, but you can do it. So great. So what? So this is one way that you can interact with the world. What Materialize is going to try to encourage you to do, though, is instead of writing de novo SQL queries over and over again, it's going to really try to draw out from you the concept of a materialized view. It's going to ask you to say, hey, maybe what we should do instead of writing this query over and over again is announce this as a query of interest. And the way you do this in Materialize is you use SQL's create view language to say, we're going to create a view, my count, and then exactly the same query from before, which has the nice property that when we go and look at it now, we're going to be maintaining this for you. And when you look at it, instead of being half a second, it's tens of milliseconds or so. And you can just update it and look at it again. You see the numbers are changing. The data are actually, this database is changing. It's undergoing a few hundred records a second of churn. And we're giving out, it turns out, nice consistent answers here. All of the answers that Materialize produces are going to be the exactly correct answer for the database at some point in time, a point in time that moves forward. So, maybe this is interesting, maybe not. You're probably thinking like, okay, count, that's pretty amazing. I could probably do count too. So let's dial it up a little bit here and do a few more interesting examples. So the next one, the first query actually from the workload we're using, this is a TPCH variant, is just a big select that uses the same relation, this order line relation, but it gets a bunch of sums and averages and counts out as well, using various SQL idioms, some filtering thrown in there as well. And it's literally just SQL 92. Nothing exotic about this query language. You can see a bunch of results up there. Don't worry about reading their particulars. We're just going to go and instead of taking 0.8 seconds like we did to issue the query, we're going to create a view. And with the view created, we're going to see that it takes a lot less time essentially to go and dive in there and get the specific data out again. Again, tens of seconds, and like 10s of milliseconds. About 50 milliseconds, 60 milliseconds in this case. You can see the data are changing. And what we've done, just so that it's totally transparent, we've pivoted the computation from one that goes and tries to pull data out of the system in the standard SQL evaluation technique to one that reacts to change. And we'll talk a bit about the architecture for that in just a moment once we've gotten through these examples. We've turned something that looks like a big database computation into something that looks a bit more like a streaming computation, a reactive computation that updates in response to change quite promptly. Now, you are all very clever people, so averages and sums and counts, again, not the world's most, you could probably figure out if you needed to how to write one of these things yourself. So I'm going to throw out some stuff which is hopefully a bit more terrifying. Here's another query. This is a four-way join. You can see in the from field, there's 4 different relations there: customers, orders, order lines, new orders. We're joining all these together with, you can see about 8 constraints down there on various primary keys. And it takes, in this case, I don't know, a second or so to compute the answer. The data sets are not massive. But we do exactly the same thing, create a view, my join up here, that is the exact same query. And now pulling out fresh results from this join is the sort of thing that I guess there's about 300 results in this join, so we're going to try to limit it down to a small number. It's again now tens of milliseconds to pop the data out. Even though the join is this weird 4-way join that involves a bunch of data shuffling and moving stuff around, once we've transformed the computation into a reactive data flow, the ability to update it is actually quite brisk, even though the original computation might have involved reaching around to all sorts of different sources, moving data around, shuffling it, what have you. So there's just a few more little blurbs here. That was revenue ascending, which is the wrong way to look at large revenue numbers. Of course, that's the most exciting way to look at them. So if we just spin the order around, we haven't really changed we certainly haven't changed the view, my join, very much. So we can get interactive access to the view by descending revenue, so we see big numbers. We can also do some other cool things, which might not be obvious. The joins and the counts we've described have been from base relations. We can write views that depend on other views. So here we're just creating a view that selects the average revenue from the results of this join. So this is now a 4-way join reduced down into total revenue and then averaged across each of the distinct orders. And when we go and pop stuff out of there, we'll see again, I hope, that it's, again, tens of milliseconds. And you can refresh this to your heart's content. It changes or it doesn't. In this particular case, we'll see we've refreshed it and nothing's actually changed. And you've probably seen that before if you use streaming systems. Like, wow, nothing changed. That's not super exciting. So how fresh is this data? Right? It's a legit question. You might ask. I haven't actually told you yet. We're going to see in just a moment. I'll point out, by the way, the third one did refresh, so things do actually change. But it's legit to ask, by how much is this trailing our input? And one of the fun things about Materialize, or at least one thing I find quite fun, is that we expose a lot of our internal system state through relations. So you can actually introspect on this and ask, what is the relationship between the times, essentially, at which each of these views are current? One of the views that we publish is this perf dependency frontiers, and we're about to sort of pull out that data. And that tells us, for each of the views that we're tracking, what are essentially the lags between the output of the view and the input to the view. And we'll just sort of read this out here. So you recall my average, which is right in the middle. My average depends on my join. It turns out that it has 0 milliseconds of lag at the time of reporting this view, which means the results my average is surfacing, if we were to query it, are exactly the correct answer for my join at the moment. My join, well, it depends on a few things. It was this 4-way join, and it's lagging a few single-digit milliseconds behind those input sources. And like, no joke, exactly correct answers, strongly consistent. These are exactly the results correct circa 3 seconds ago. So anyhow, this hopefully gives you a sense for some of the capabilities of something like Materialize, writing interesting, complicated SQL queries involving joins of many relations, and actually insisting on and receiving relatively low latency guarantees. I'm hesitant to say real time because everyone else is not hesitant to say real time, but quite fast, faster than basically other systems. So, okay, that's the demo. I think it's worked out great. I'm going to show you a few other things. So this demo was picked because I imagine that several of you might resonate with sort of CLI type tools, or at least not be as allergic to them as other people. There are other ways that Materialize presents. So this is some open source BI tools out there. This is Metabase in particular, but because Materialize presents as something that looks a bit like a relational database, looks like Postgres. Currently we're using PGWire. You can attach other types of BI tools to Materialize, and they're currently programmed to think like, well, a query is going to take about a minute or two. I better not do them that often. And in the case of Metabase, we had to dive in there and convince it to refresh once every second instead of once every minute, because we can handle it just fine. But if you imagine using the existing crop of BI tools, if you're familiar with them, in a much more interactive manner, something where you actually watch the data change second by second instead of hitting refresh once a minute and scrubbing around in the data, that's sort of the look and feel that we're going for. So with this in mind, what I thought I'd do with the remaining time is talk you through a bit more of the architecture underneath the system to get you, if you're currently thinking like, wow, that's amazing, I wonder how he does that stuff. I'll talk through that. If you're not thinking that, I'll ask you to watch the first part of the talk again. And so let's talk a bit about the architecture. We're going to return to that picture before with the relational database. It's going to show up on this slide. I've described Materialize here visually as 3 different layers. Don't assume anything about the ordering. It's just the picture works out better this way. So at the bottom, at the sort of the access point to Materialize, we have a bunch of clients. These are the SQL clients, a lot like the CLI that we saw in the demo, where someone just connects and starts typing. Similarly, someone can just connect and start typing. SQL, or in principle, other sorts of interfaces. If you're using something like Metabase, it's also going to connect as a client and start asking queries and building up session state and prepared statements and stuff like that. All of these clients go into a coordinator. So this is a central access point for Materialize, and this is a moment where essentially all of the clients can indirectly interact. So they share state a little bit. They can reuse the same views and names with other clients. So if I created my join and I yelled out to someone, hey, Craig, by the way, who's also here from Materialize, sorry, I should have said this. And Craig's like, oh, sweet, my average equals ... This works totally fine, right? So we share all these things. If you have this collaborative data analysis team that some people build some views and just ship them over to other people, works great. The coordinator is what mediates all of that. It's also what decides if 3 of us want to call something my join at the same time, who wins, and basically provides guarantees of consistency and durability and whatnot that an actual database would be expected to provide. And up top, we have timely data flow workers. And if you're familiar with the work that I do, this is where I show up. This is the data parallel compute backplane. And that is what's going to get all of this work done. All of the incremental view maintenance, high performance, high throughput stuff happens back there. So when we look at how we interact with these layers, the clients is SQL. I put SQL actually. This is not a SQL-inspired language. This is not SQL with a bunch of caveats where you can only do insertions. It's not SQL where you need to know what's a stream and what's a table or anything like that. It's SQL. You write a thing in SQL, we give you the correct answer. We maintain the correct answer no matter how your data change. Insertions, deletions, don't care. It's SQL 92. If you need with recursive, talk to us. But the intermediate representation that it then goes into, we do some standard database analysis at this point. The world is a little different in the streaming space. A lot of the analyses you would do in a database, essentially, are targeting other performance characteristics than what we're worried about. So we're very worried, for example, about the standing memory footprint of these queries that we're going to install this data flow. That's a thing that a database doesn't necessarily worry about too much because queries are ephemeral. So we're going to be looking a little differently at these queries to make sure that the system doesn't fall over. And then up top, the timely data flow system uses a framework called differential data flow, which is work that I've done in the past that's really good at incremental maintenance of relational data parallel computation. So things like joins and aggregations and what have you. And these connect to the outside world in sort of schematically the same way we saw before. There's a relational database that's pretty loaded with a bunch of work going on. People are buying things from you, or people are visiting your website, or your logs are spitting out information. All of that information flows into Materialize. We're currently using a bridge called Debezium that drops things into Kafka, but there are a lot of ways that, in principle, you can get data into Materialize. It's a pretty simple format. The horizontal lines here are the data plane. So this is meant to be this high throughput, low latency, and generally solid, strongly consistent compute infrastructure going this way that is controlled by the control plane, which is this vertical dimension. So clients come in, they talk with the coordinator sets up some data flow, and then the data just move through that as promptly as possible, as fast as we can manage, essentially. And on the right-hand side, if you want to write this out to something like Kafka, that's great. The clients can also just interactively peek at this data and look at it and see what's in it. But if you're looking for high-throughput data transforms, sending it back out to Kafka is totally sane. In principle, we could also present as a read replica for a database. That's not something we're currently doing, but we have lots of options. If you're interested, definitely let us know, because we have a lot of we have some free cycles to think about what we want to do next. So what I'm going to just sketch out is some of the cool internal architecture to the Materialize compute backplane that makes it different from a lot of the other systems you might be familiar with. Different from things like, let's say, K-streams, or different from Flink, different from basically just about everything else. One of the big important differences is that in timely data flow, we're going to be building up data flows. I'm going to start drawing pictures of data flows in just a moment. But the data flows are all sharded in the sense that we might have multiple workers. Let's say there's 4 workers in this picture. Each of them are going to be executing the same data flow. They're going to be executing fragments of exactly the same data flow. We're not going to partition up work between the workers. When we say join, all of the workers are going to help out computing the join. When we say reduce, all of the workers are going to help out computing the reduce. There's a good reason for that, and the example is going to try to build up and show you what that good reason is. So let's just start out. You might have created a source here, orders. I've just made this up, but in Materialize, you would announce a source, which is something like, let's say a Kafka topic that's meant to hold some sort of change log coming out of your relational database. We'll run off and we'll grab that and we'll start pulling in the data for you and drop it into a named thing, orders here. So schematically, these green widgets represent materialized sharded indices. And this is one of the important concepts in Materialize. So these materialized sharded indices, there's 3 words in there, they're all important. So they're materialized in the sense that we have actually collected the accumulated changes that have gone on, and we're sitting on it. So if someone comes and asks us now, hey, tell me about orders, like I'm super interested to hear about orders, what's the count of everything in orders? We need to actually have that data around, right? If it washed past and we let it go, we don't really have an answer for you anymore, and we feel really bad, like we're not giving you the correct answers anymore. So this is absolutely going to materialize the stream that has come through. We're going to accumulate up all of the changes, pluses and minuses, and keep a representation of the current state of affairs for orders, and in fact, a little bit of historical detail for it. It is sharded in the sense that the 4 workers in this picture are each maintaining roughly 1/4 of the data. And if you want, you can think about this as being sharded up by like primary key or something like that. If orders have a primary key, we will have distributed those keys across each of the 4 workers, and each worker is now roughly handling about 1/4 of this data. And they're indices in the sense that they are, in every case, going to be indexed by some important quantity. If it's a primary key, that's a great example. We'll index them by primary key, so that in the future, if people need access to this data by primary key, a common thing in a join, we'll just have access to it ready to go with no additional data manipulation required. So we'll see a few more of these materialized sharded indices. Again, they're a pretty important concept. I'll call it a few more reasons that they're important. But let's imagine someone shows up with another source, orders and customers, and we then get asked to join them and reduce them. And I just imagine that sales, so I had a bunch of other things, but it turns out like putting sales and profit and stuff like that on the right-hand side makes people feel really good about things instead of like defects or what have you. But throwing down these additional bits of data flow can be relatively cheap if we're already sitting on these materialized sharded indices. Imagine a world, this doesn't make a lot of sense in this example actually, but imagine a world where orders and customers were both sharded by their primary key already, and we are joining on these keys. That doesn't make a lot of sense because they're primary keys for each of the relations, but bear with me. We would not need to move any of the data associated with orders and customers around. They're already co-located appropriately on their workers, partitioned by key. Thank you. And we're good to go, essentially. The operators here, things like join and reduce and whatnot, are all designed to be these reactive implementations that as changes flow in from the sources and into these indices, but the indices also present changes outwards, they're implemented as operators that are able to produce the correct output changes. Right, so as, let's say 5 new orders show up, the join operator is going to be smart enough to say, ooh, those might match with the customers. I better look up and see if these 5 things hit over in customers and produce any new matches in the output. If a customer is retracted for some reason, I don't know why, maybe they're not so happy, the join will need to think about, should I be retracting anything from my output? The reduce similarly will update their aggregations, their accumulations correctly at the same time. So let's show a cool case of these sharded data flows being used excitingly. I've just put together another parts source, and let's say now that I want to join that with sales. Sales is that Materialize index over on the right there. These are the same thing. Not only are they conceptually the same thing, Materialize, they're actually the same in-memory index. So if someone wants to start using sales, they just grab that pointer and start working with it, which is really cool. Sorry, I mean the Materialize system in response to them typing join. But we're able to just grab this pointer and start working with it rather than reflowing the full contents of sales off to some other machine that's going to build up another index of it anywhere, or anything like that. So if we had a join, hypothetically, with sales, and imagine that parts was, I don't know, relatively small. So sales is, let's say, gigabytes, and parts is a few thousand records. Turning on this data flow is a matter of milliseconds. It's just a matter of synchronizing between the workers. We don't actually have to flow sales anywhere. And the 1,000 records that come in from parts, 1,000 sort of changes from the initially empty collection, just result in lookups and sales, and you actually get the answers back if there's only, let's say, thousands of records and parts in, again, milliseconds or so. So you're not actually regrinding through these large data sets that you've already maintained in indexed form. And this is perhaps one of the most important points of departure from other systems in the space that have adopted, to their credit, these pure streaming architectures where there is no persisted or maintained state. There's a downside to that, and that is regrinding through these large volumes of data each time you need to use them. So let me explicitly call out a few good things that these things do, and then I'll wind down and we can sort of swing into question answering, asking and answering mode. So the main point, technical point I love to make here is that these materialized sharded indices improve several things. So they improve throughput in the sense that instead of keeping 5 copies of one indexed collection, we're just keeping 1. That means that we do a lot less work as we're receiving new data. We can handle higher loads of changes coming in. They improve latency in several ways, but query latency is one that I just called out. So the amount of time between you finish typing the query, you press enter, and we're able to start giving you answers back is potentially a lot lower if we're already sitting on the indexed representations of the data assets we need to start answering the questions. So this takes things from potentially multiple seconds down to milliseconds if we're working, especially if you're interrogating large collections. So if you're going in and saying, like, I'm really interested in this known subset of people who've complained or sent me emails in the past day, I want to go and look up what their experience was. A relatively small set against a big set, this will come back in milliseconds and continually update, as opposed to spinning up a data flow. You can tell me how long those take. A really important thing that I think not a lot of people look at is query scaling, meaning as more and more queries show up, so as your data analysis team grows, if it's just one person asking one word count query, great. We can draw that on the board. If it's one person asking 5 queries or 20 people each asking 10 queries, what are the resources required for that? Do you actually need to get, in that case, 200 times as many resources as for that one data flow? And one of the really nice things that goes on in Materialize is that if people are reusing the same data assets, they can start asking more questions. So long as the number of distinct uses of the underlying data aren't necessarily growing, or at least as those grow. Thank you. As those grow, you need more resources. But if people are just reusing the same customers relation, the same source data files, you don't necessarily need to invest in a lot more resources. So there's a lot of really nice sharing that happens that makes query scaling increase, larger teams without blowing your cloud budget. All right, so take home points. This is the last slide, and then I'm gonna stop. One of the goals of Materialize is to try to encourage people. May not be the right audience, but try to encourage people to replace some of the microservice morass out there, which is a lot of people writing thousands of lines of Java, trying to make sure they covered the various cases of people reading from this to the other. To the extent that you can replace that with 10 lines of something like SQL that just declaratively states, this is what I want, someone else is going to handle making this work out correctly, great. You don't have to stop doing the stuff that you like, but you can focus more of your attention on the hard cases. Let the easy cases be handled by a system that sort of means to do this well and has put a bunch of engineering in it. So outsource the complexity of the easy things that you can describe to us, essentially. And there's a new cool thing that you can do that I'd love to get people starting to think about, which is this interactive analysis against live data. So in a lot of prior systems, either the data comes in relatively slow chunks, once every hour or something like that. Your data warehouse gets refreshed only so fast. Or in streaming systems where the data moves fast, your ability to launch a new query and get results back is gated a bit by the time to build and deploy these data flows. We're actually able to do both of these in sort of millisecond timescales. So you have the ability to interactively explore data and learn about it and understand it and ask, what question do I need to ask next and respond to the data that I'm just seeing interactively. Like a lot of you are probably familiar with DevOps style problems. Something is on fire in your computers. How long does it take you to figure out what the answer to that is? You start asking some questions. You really want to know what the current state of affairs is. As soon as you see that, you think of a different question to ask. Right? There isn't just a standard battery of questions you need to know. This is something that we think is really opening up now, and we love to try to get our head around what are all the exciting use cases here, how much power does this give people, what would people do with it. So I'm going to wind down there. I apologize, I went a little bit late. But there's some contact information. You can read all about us here at Materialize.io. Actually, there's a few places to check out online. Materialize is one, that's us, the organization. The underlying compute substrate is all publicly accessible, open source, all of that stuff. You can find that at Timely Dataflow on GitHub. I'm Frank McSherry, Chief Scientist at Materialize. Feel free to contact me using my very professional email here. And if you'd prefer to be unprofessional, my Twitter handle is down there, and this is a great way to bait me into responding to your concerns in a more public forum. But I'm going to stop with that. I appreciate the time you've given me, and we have, I believe, some time for questions.
On the very left side, that's like one database. Can you materialize data from like multiple databases?
Yeah, so okay, good. The question is, if you're just mirroring one database, the story might be relatively easy. What happens with multiple data sources? It's a great technical question. Operationally, the underlying compute substrate can. There's the differential data flow substrate handles this cool thing called multi-temporal data flow, where so if you like, think of the timestamps in each of these systems as the commit IDs, like a GTID in MySQL, which is sort of consistent view of the database, consistent view of the database, consistent view of the database. If you've got two of these that are marching forward that are unrelated, you need some sort of story about how do I talk about these two different notions of time at the same time. And as best as I understand, the academic underpinning of this is this concept of multi-temporal analysis, where you have essentially two dimensions of time. They happen to go along largely together, but you need to think about them separately. The underlying substrate supports that. Materialize itself at the moment does not. Our times are integers, but it's easy enough to think about changing that around as people show up and say this is crucial for us. I don't know if that's the short answer is not right now, though we'd love to know if that's important. We totally could do this given enough time, and like if everyone in the room said yes, that's what we need, we would absolutely go and do it right away.
Thank you for your talk. That was great. One question, maybe two questions, to be honest. The first one, you mentioned that you stream or you get changelog. You mentioned changelog through Kafka to your system to Materialize. And the question is, do you mean by changelog the write-ahead log, which is a technical term for from like the change set in relational databases? And if yes, then how you monitor that, how you really like stream that, how you connect to that to push it into Kafka. So the first question, and the second question is, the demo was great, but I noticed that when you create a view, it takes some tens milliseconds. And is that real? I mean, or is it just the execution or the parsing SQL, and then in the background is the whole like real materialization of the view?
So great, two questions. So the first one has a very easy answer. There's an existing project called Debezium that means to be a bridge from several different existing databases into a Kafka changelog style feed. So they're monitoring the bin logs, and depending on the particular database, the write-ahead log. In some cases, doing a little bit of magic there, because not all of them present exactly the right information, but they present a stream of, for each record, the before and after view of that record. In the example, the demo, the view creation, absolutely, you're absolutely right. That is setting up metadata, and it's building the data flow, and it's starting to stream data in. So if I were incredibly fast at typing, I could have created a view and then looked at it immediately, and you might have seen data that was a bit stale because the view had not yet fully populated. This is what we use these, like the last part of the demo was information about the lag on these things, and that's something that would initially, at the moment of creation, show, wow, quite a lot of lag. Like we often see something like 47 years of lag. I guess 49 years of lag now, because when it starts at 0, that's Unix time. But pretty quickly these things fill out. Sorry, you're behind someone. These things fill out, and absolutely you want to dive back into that logging reporting relation to make sure that you see the right stuff there.